And let's do a share screen. Hello, Shukai, how are you? Can you see my screen?
Hello?
Ah, now you see it. I hope you. Can you see anything or you don't see?
We don't see it, a black screen.
Okay. Why don't you see? What's going on here? Let's try to do again a share screen. Ah, now can you see it?
Yes.
Yes.
Okay, very good. All right, so we're gonna have a busy meeting today because basically it's not actually that busy. It just covers two separate subjects. So last time we were discussing, we finished up discussing the strong interaction. We started to discuss the weak interaction, which, as I said, is presumably the most interesting one of all because it contains several features which are unique to this interaction. But now we're going to start again. I'm going to start by the tutorial simply because I'm not sure how long it's going to last. So I don't want to end up with not finishing it. And then we will resume with the weak interaction. We'll continue discussing things such as parity and the masses, which are quite interesting. But first thing first. So we start with a tutorial. So the current tutorial, and as I promised you, I'm going to give you another homework every week until the end of the semester, basically, which I think is good for you, right, to practice that. So the tutorial today is about particle acceleration. Particle acceleration and detection. Really, it's to give you a little bit of taste about accelerators. You know, when all these theories are very nice, but at the end of the day, you need to be aware of the fact that, you know, again, as I keep on saying to all my students, right, physics is, at the end of the day, this is an experimentally driven subject, right? The theory, beautiful as it may be, is only accepted if it fits into the experiment. Then myself, so I do the experiments. Without them, it's kind of meaningless. So I want to say a few words about accelerators. I'm sure you've all seen that. I mean, you've all heard about them. Because of the way it is right now, I can't get the head properly enough. Show you some pictures from CERN and other places. I've been there. It's quite amazing, I have to say. It's hidden down there underground. You go upstairs, it just looks like a field with cows and everything. You know nothing, and then you go down and you feel like you're inside the James Bond movie with 10 stories building underground, 50 meters below ground. And I can just describe how amazing it is, but we're not going to do that because we don't really have much time. Instead, we're going to say a few words about the physics of the accelerators and about the physics of the detectors. So let's start by saying a few words about the accelerators. So, you know, there are various accelerators, colliders, and they can be specified by a few features. So the features that differentiate between the accelerators, they are characterized by, right, so which particles are being accelerated, right? Could be an electron, positron, right? Proton, antiproton, proton and heavy nuclei. Right, there are many. There are a few in Israel as well. Of course, not as big as the one that we have, but for heavier nuclei, we have plenty of those. The second question is about collider versus a fixed target. Right, fixed target, we mean that there is a particle that is being accelerated, and then it's going to hit a fixed target. Collider means we have two beams of particles, and they're being accelerated in the opposite directions, and then they collide with each other while they're both moving. So that's the technical difference between collider and a fixed target. The other one is circular versus linear. And of course, the most important is the center of mass energy. All right, the square root of S, which we discussed. That's the most important thing, I guess, right? The most notable one, right? What is the energy that one can get to? And of course, the luminosity. So a few words about the luminosity. We've already discussed that in one of the previous weeks, right? So it was defined as relating the cross-section for a given process to the actual number of events that's going to happen, right? So the NDT is the actual rate of collision events that's going to happen, is the luminosity times the cross-section. I'm using curly L similar to the Lagrangian, but of course this is the luminosity. This is the cross-section, right? If we have two beams, right? So for two beams, right? And then the luminosity, right, is just the total number of particles in the first beam times the total number of particles in the second beam, divided by the cross-sectional area, right? And the rate of collisions, right? F is the collision rate. I'm going quickly because we already did that. So if you have any questions, then please stop me. Right? So for two beam collider, that is. If something is not clear, I assume this is things that are relatively simple, and we've already discussed some of them. So if something is not clear, then let me know. Now we can have a similar definition if we have a fixed target experiment, right? So if we have a fixed target experiment, right? So if we have a target of density and target particles in the target, in the target, right? And then the width of the target is delta x, right? Then we simply take the N2 over A, and just name it as just NT delta x, right? So the luminosity is just N, the number of particles that are accelerated, times NT delta x times F, or N times rho times NA over MA times delta x times F. Right, the units of L, it's centimeter minus 2, second minus 1. Right, everything is clear? Yeah, no, maybe? Yeah? And sometimes we talk about integrated luminosity. Right? Integrated luminosity L is just integral of L dt, right? Integrated over time, which of course have units of centimeter to minus 2. All right. And it's used when you want to consider the total number of events, right, during the time of the experiment is working, right? So the total number of events right, during the experiment, right, L is, N is L times sigma. By the way, just to give you a feeling, right, you know, that we'll discuss Higgs, start discussing it next week, I hope, after we finish with the weak interactions. You know, it was detected a few years ago, and then it was a Nobel Prize, of course. How many Higgs particles were detected, do you know? Total number. that they could claim a firm detection that was worth a Nobel Prize. Does anybody have a clue? Do you want to guess?
$50?
Sorry? Go on.
50 years?
I could not, I didn't understand what you said. How many?
50 years?
I'm sorry, I don't understand what you're saying.
Can you hear me?
Yeah, I hear you, but I didn't understand what you said. Can you say it again?
That's how many years it took to get the prize, right?
How many years? Yeah, it was about a year, something like that. Of the order of a year. So, what's your guess? Hey, come on, guys. It's not the exam. You have to think too much. Just give some guess. Do you hear me? Yeah, come on. There are only 4 students around here. How many do you guess? Come on. Should I go one by one? Throw a number.
50?
50. Another guess? Oh, come on.
Was it actually the Higgs itself that was detected, or was it its decay product
It was the Higgs itself, yeah.
itself?
What? How much?
I don't know, a few hundred maybe?
200 maybe? Yeah, someone else want to try?
I guess 10.
Like 10, yeah? And one more guess?
50.
50? No, we had, yeah. The number is 6. And that was enough for Nobel Prize. The expectation was 4, and that fell within 5 sigma. Okay. So let's do a quick question about that, right? So in 2018, so question number 1. During 2018, the LHC collected data corresponding to 80 femtobarn minus 1, right? Now, this is LHC is the Large Hadron Collider, so it collides protons. It's a proton-proton collider. So the total cross-section for the PP collision is 100 megabarn, millibarn, sorry. The total cross-section for PP collision is 100 millibarn. Then what was the collision rate in the LHC during the year? Okay, so the solution is quite straightforward. It's just putting down the numbers, right? So the luminosity, right, is 80, right? 1 over femtobarn per year. So, right, it's 80 divided by 60 seconds, 60 minutes, 24 hours, 365 femtobarn per second, which is 2.5 times 10 to the minus 6, 1 over femtobarn per second. Now, you just have to multiply by sigma, and so the n over the t, right, is just L times sigma, which is just 2.5 times 10 to the minus 6, 1 over f femtobarn per second, times 100 well, femtobarn times 10 to the 12 femtobarn per millibarn. Hope I didn't mix anything. Yeah, that's fine. Which give us 2.5 times 10 to the 9 events per second. Or in other words, the PP collision rate was one collision per or each 4 nanoseconds. Right. Now, the problem, of course, now you can start getting a feeling of the technical problems involved, right, in an experiment like CERN, because this is an extremely fast rate, and then electronic systems are not capable of recording all these, because any electronic system has some finite response time, right? And also the storage time you cannot store data at such a rate, right? So that's why the way this system works is using a triggering. So you trigger the system only when there is something which you think is interesting. All right? Good. Now, so that's the need for trigger system. Now I want to speak about the circular collider. So obviously, you want to accelerate the particles. The way you do it is via electric field. If it's linear, then you accelerate them once. Circular means that they ring all over. So in order to keep them ringing, right, then you have to use a magnetic field. These are charged particles, so it's quite easy, reasonably easy. So in the circular collider, we have electric field accelerates, and magnetic fields that governs the motion in the perpendicular direction. So the equation of motion, right, classically, for the accelerated particle, it's a classical one. I'm sure you've seen that. F, right, it's just QVV, mv squared over r, which means that QB is mv over r, which means that the momentum mv is QBR. Right, that's the maximum momentum that you can have there. This is the non-relativistic. Relativistic one, you'll develop at home. So if we take the momentum P, right? If it's in unit of GeV, take P to be in GeV and B to be in Tesla, then we get to the required radius, right? R is P over 0.3B, which is kind of handy. That relates the radius of curvature to the momentum of the particle and the magnetic field that you have there. Okay. Now, what's the main problem? What's the key problem with this accelerators? Actually, there are many problems, but what is the kind of the immediate one to see?
How do you time them hitting each other?
Oh, that's quite easy. That is not so problematic. Relatively easy. There is a much more severe problem.
Radiation?
Radiation, exactly. Radiation losses. Right. If you take a particle, you should have seen that in one of your E&M courses, maybe advanced E&M, right? If you take a particle and it's rotating, so it's accelerating, right? You have a charge that accelerates, essentially, right? A charge that accelerates emits radiation, right? And if you have a charge that accelerates in a magnetic field, so magnetic field, you know, and forces the charge to go in circle around the magnetic field, right? Then what type of radiation is going to get out?
EM.
Electromagnetic. Yeah, how do you call these electromagnetic radiation? You know? I think you should have learned that in your E&M course. I think. That's a cyclotron radiation. Now that I mention it, did you see it before? No? Okay, now I'm surprised a little bit, but okay. You sure you never saw cyclotron radiation? Okay, I'm not gonna hold it against you, right? But a charge, an accelerated charge emits radiation, right? If a charged particle in magnetic field right, emits what's called cyclotron radiation. Who of you have seen cyclotron radiation? Please raise your hand so I can see. Nobody? Okay, next year, first semester, I'm going to give a course in plasma physics. You're all welcome to come. Then we'll discuss charged particles and their motion in fields. Okay. Now, this is cyclotron radiation is for the non-relativistic particles. Synchrotron radiation. So the relativistic version is called synchrotron. I'm not going to develop it for you right now. I'm just going to tell you that the total power radiated by a charged relativistic particle in regular units, so the total power P gamma is just 2/3 C times there is a constant E squared over 4 pi epsilon 0 for the SI units, and then beta 4 gamma 4 divided by R squared, or 2/3 C alpha, the fine structure constant H bar C, beta 4 gamma 4 divided by R squared. If you want to put the values, then we get this is about 3 times 10 to the minus 10 beta to the 4 gamma to the 4 divided by R squared in units of GeV times meter per second. Now, since gamma is the Lorentz factor here, right? Gamma is just E over. That means that the power P gamma goes as m to the minus 4. Which means that the lighter particles, such as electrons, they lose their energy to synchrotron much more rapidly than protons do, which is one of the advantages of using the large proton collider or hadron collider. Right? So let's do a small exercise. Question number 2. Right? The LEP, that's a different experiment. LEP in turn, it's a circular electron-positron collider. It was a circular E minus E plus collider. Right? It was working during the 1990s, roughly. Now the radius, it was 3,096 meters, and each beam contained n of 3.1 times 10 to the 12 particles, right? And the beam energy was 45 GeV. That was the energies that were reached. and the particles were revolving inside the collider at about 7,000 hertz. So the question is, what was the energy consumption of the collider? Or in other words, what was the power required to supply to the collider in order to keep the particles in their course? What is the energy, power required to keep the particles in the course? I'll write it down. So the solution, LEP. So the energy lost by a single particle in one round, right? So energy lost in one round, energy lost by a single particle in one round, delta E, right? P times T. So it's P times 2 pi R over beta C. Now these energies, and this is something which I don't want to see in the exam, right? In these energies, you can simply take beta to 1, right? Beta is 1 because the particles, when I speak 45 GeV, you can start calculating and you end up that beta is 0.9999 something, right? They just move at the speed of light. Beta is 1. So we can write down that delta E per single electron, right? P dot T is just 2/3 C alpha H bar C beta 4 gamma 4 divided by R squared times 2 pi R over beta C. So this is just 4 pi over 3 alpha H bar C beta cube gamma 4 divided by R. So just put in the numbers that we plug in, right? So it's just 4 pi over 3 times 1 over 137 times 0.197 times 10 to the minus 15 GeV times meters times, now we have 45 GeV, and the mass of the, what's the mass of the electron in GeV? What is the mass of the electron in GeV?
1/2 MeV.
1/2 MeV, right? Electron is 2,000 times lighter than a proton, and the proton is 1 GeV. Okay? Not exactly, but good enough. So divided by 0.511, it's actually 511 kV times 10 to the minus 3 to the power 4. The beta I neglect. The R is 3,096 meters. Plug in everything, and you end up that this is 0.117 GeV or 117 MeV. So that's the energy loss per particle per round, right? We have 2 particle beams, n particles in each beam. Yeah.
Just to clarify, in the test we can take beta to 1?
Depending on the problem. If I give you a problem in which the energy, right, of an electron is or a proton is much, much greater than the rest mass, then yes. Right here we're speaking about 45 GeV versus 0.5 MeV. Okay. So obviously beta is 1. If the energy was close to MeV, then you couldn't do it. Or you'd have to justify that. Right. So the total power, P total, right, delta E times the N times 2 times F, right? Frequency. So 117 times 10 to the 6 electron volt times we can convert it to joule, 1.6 times 10 to the minus 19 joule per electron volt, right? Times 2 times 3.1 times 10 to the 12 particles times 7,000 times per second. So that gives roughly 8.12 times 10 to the 5 joules per second, or 812 kilowatt. They pay quite a large electric bill in CERN. In fact, it's not like that, as I was told when I was there. They sit down on the French electric, what to say?
Power.
Sorry?
Power grid.
The power, yeah, the French power. And in fact, they don't use it. They don't make these experiments during the summertime or holidays when there are the peak times in the electricity, because they get to I don't know how many, a considerable fraction of the total capability of electric power production in France overall. Okay, I should mention that the newer one, right, the LHC, it's much less, right? So for the LHC, well, it's much less. It's 4.5 kilowatt. Although they reach higher energies, they're using protons, which are much more efficient, right? Because we have the ratio of m electron over m proton to the 4, right? So it's about 10 to the minus 13, which they're gaining. And of course, it's a different, the total number of particles in each bin is much greater, but the frequency is different. Anyway. Yeah. Yeah.
Sorry for taking you to this corner, but 8 kilowatt isn't much.
Not for that one.
No, you said kilowatts is like a consumption of a large house or something.
Yeah.
I think the end consumption is for cooling the superconductors.
You know what? Maybe you're right. Maybe you're right.
Because 8 kilowatts is like, I don't know, $1 per hour or something like that in an electricity bill.
Maybe you're right. What I told you about the consumption is true, but possibly not for this one. Possibly you're right, and that the main consumption is for the cooling of the superconductors for the magnetic fields.
Okay.
Maybe. But thank you for that. Oh, what happened? Okay. Another question that I want to focus. I told you I'm a theoretician, so when they show me that, I'm saying, oh, that's really cool. Another question. Fixed target versus collider. So let's say that we have a proton with energy E much greater than MP, which collides with another proton at rest. Collides with a proton at rest. All right. Now, what is the total center of mass energy? Right, square root of S in the collision. And part B of the same question is compare the results with the results of true protons moving against each other, but with energy half E. Okay, so this should be quite easy for you to answer by now, I hope. Right? So part A, right, in the lab frame, we write down the four momentum. P1 is E and P1, and P2 is just M and 0. So S in the center of mass energy, right, is just P1 plus P2 squared, just plus M squared minus P1 squared, right? So this is just 2M plus E. I think you practiced that in one of the first homework. For part B, right, the lab frame is the center of mass frame. So P1 is just E over 2 and P1, and P2 is E over 2 and minus P1. So S, right, P1 plus P2 squared is just E over 2 plus E over 2 squared minus P1 minus P1 squared. So this is simply E squared. So if you compare them, right, SME versus SEE, right, it's just 2M squared plus 2ME over E squared for E, which is much greater than M. And we can remove the first term. This is just 2M E over E squared. And the square root to take the available center of mass energy, right, square root of SME over SE, just be square root of 2M over E. So the collider experiment can gain us a huge factor of energy, right? We get the square root of E over M. That's what makes them much more preferable. All right. Yes, no, maybe?
Yeah.
Okay. The last thing I want to do, while it's still going to be a little bit, is the detection of particles. So particle detection. Okay, how do we detect a particle? Right, okay, so we take particles, we collide them, right? So there's this big collision, right? So there's these two beams of particles, they collide. But now we actually need to see that, right? So we put around it a detector. Now, the detector is made of various materials, right? But the basic way of detecting, right, is just to you know, the fact that the particles interact with the matter in the detector, right? The detector is made of some material, be many different materials depending on the experiment, and the particle that is being produced in this collision is interacting. Now, the first thing to note is that we cannot detect all particles, because if particles have a lifetime which is too short, right, they will decay before they reach the detector or before they have time to interact with particles in the detector. So often we don't even see the particles that we're looking for. We just think that they're daughter particles, right? The decay products, right? So in fact, there are only very few particles that are actually being detected in the detector because their lifetime is long enough to be detected. So when we discuss detection, we talk about detection. right? What is usually being detected is either stable particles, right? There are only very few of those, right? Electron, proton, neutron. Or particles that live long enough, right? Particles that live long enough. Right, like muon, pion, tau, kaon, few more, not that many. Right, because when we have a particle like, heavy particle have too short of a lifetime, right? For example, the W boson, which we discussed, W boson, right? The lifetime is 3 times 10 to the minus 25 seconds. That's way too short to be detected. It's part of the reason why it was only seen in the 1980s, right? 83 was the first detection. Right. So that means that the W boson, for example, will decay way before it even enters the detector.
This is the lifetime in the rest frame of the W boson, right?
Of course. Yeah. But that's still, I mean, see what Lorentz factor you need to bring it to get a reasonable value, right, of size, right? Just multiply by C.
Oh yeah, of course. It's still very small, but it still makes a difference.
Right. So what happens when these particles that we can detect, how do we detect them, right? So they pass through the material in the detector, right? And they interact with it. Now, the main way they interact is by ionization, right? So the dominant energy loss of the particles is by ionization. Right? That's actually by particles, but mainly by muon and the proton. It's not all of them. So what I mean is that charged particles of masses m, or much greater than the mass of the electron and much more than the mass of the nuclei. So what happens is that when you have a charged particle that travels through the material, it transfers energy to the material, right? So majority of the energy is transferred to the electrons, right? And what happens is that it frees them from the atoms, and this freeing of the electrons, this is what ends up in a measurable signal in the detector. The nuclei themselves don't get much of energy. So the average energy loss to ionization in matter is given by a formula which is quite famous. It's called the Bloch formula. So the E over the X is given by the Bethe-Bloch formula. The E over the X is minus 4 pi RE squared ME C squared rho N Avogadro Z over A Z squared small z. This is a big Z and this is small z. Z squared over beta Z squared times, now we have a correction, logarithmic correction of 2m E C squared beta squared gamma squared W max divided by L squared minus 2 beta squared minus delta beta gamma over 2. Let me tell you what each thing means here. So R is the classical electron radius. Z, small z is the atomic number of the incident particle. And capital Z is the atomic number of the absorber. Na is the Avogadro's number. Rho is the mass density of the absorber. A is the atomic mass of the absorber. And L is the mean excitation potential. Approximately 10 times the electron volt. And W max is the minimum energy transfer in a single collision. So it's also given by some formula 2 MEC cubed beta squared gamma squared divided by 1 plus 2 gamma ME over M plus ME over M squared is the minimum energy transfer in a single collision. Well, it's not a delta function. It's a density effect correction to the ionization losses. It depends on the material. The units are GeV over centimeters, right? Units GeV over centimeter. Okay, now I prepared in advance here. This is how it looks like. This is for muon. This is the minus the EDT, right? For positive muon in copper. So muon in copper stopper. And that's basically how it looks like. So the first term, right, the Z squared over beta squared term is dominates for low momentum particles, right? This is this part, right? So Z squared over beta squared dominates for low momentum, right? And then the minimum energy loss is here, right? Minimum ionization. It's about gamma beta equal 3. That's the minimum energy losses. Right? Particles that have these energies are simply called minimum ionizing particle, or MIPS. And as beta increases, right, you get the logarithmic term which becomes dominated, which gives the relativistic rise. So again, let me give you one example for a question. The rest you'll do at home. So let's look at the atlas. So the question that we're going to have. Okay, so the atlas detector return is ground. right? Now, the question is the following. What is the minimum energy required for cosmic particles, for cosmic muon, to penetrate the ground and reach the atlas without being stopped by the rock above it? For cosmic ray muon to penetrate the ground. And reach atlas. Now you can assume that the ground density rho is about 2 grams per centimeter cube. And that, of course, that can also safely assume that the muons do not decay on their way to the detector. So the solution is to treat the muons as the MIPS up to quite high energies. So we can also use that here. Assume muons or MIPS. So if we look here at the figure for a MIP muon, it's going to lose roughly of the order of 1.5 MeV per centimeter. So for MIP muon, it will lose something like 1.5 MeV per centimeter, right? But this is in a material of density 1 gram per centimeter cube. Now, for the rocket we have, the density is double. So that means it's going to lose something like 3 MeV per centimeter. So when traveling 50 meters, it will lose like 3 MeV per centimeter times 5,000 centimeters, which is 15 GeV. We can take the minimum energy to be roughly 15 GeV. Now we argue that the muons are MIPS. We can look to see whether this assumption is valid, and we see that for 15 GeV, which is roughly around here, right, the penetration depth, right, it's not exactly 1.5, I assume, MeV per centimeter, but 2 MeV per centimeter. So, the values are not that different. So the assumption that I made in solving this problem was a reasonable one. Right, up to orders of magnitude. I mean, it's 30%, fine. Questions? Is that clear what I did? Questions? Anything?
By assuming it's a MIP, you could basically take this part of the graph and use that in your equation.
Yeah, exactly. Yes, here. Not of the easiest. Because there is a logarithmic correction, so I have to go to quite high energies to get it done. All right. More? See, some people were here and then they're gone. I'm not sure what happens. Maybe there's some communication problems. Okay, I don't know. Okay, do you want to take 2 minutes break or do you want to move straight to the, so I'm finished with the tutorial. This is the end of the tutorial today. I'm going to post today or maybe tomorrow because I have some busy afternoon. I'm going to post the next problem set, which will deal with that, with detectors. That's because we didn't really have too much time to discuss it. So we'll discuss it. You'll work through it at home. Any question? Do you want to take a 2 minutes break before we now resume to the lecture, or shall I just proceed straight to the lecture? It's an open question to you guys.
2-minute bathroom break would be good.
Sorry?
2-minute break would be good.
2 minutes break. Okay, now it's 2:59 my clock. We'll be back. You can go to stretch yourself and go to the toilet or whatever, and we'll meet here in 2 minutes. I mean, I'm going to stay here. Shukai? Hi.
Hi.
When are you going to have time to meet for a meeting?
Yeah, after your email, can I meet you in Sunday?
Sunday? Okay.
Yeah.
I have a meeting in the morning. I think it should be over. We can meet at 11, I think, my time. Local time.
Okay, it's okay.
It's okay?
Yeah.
If it's delayed, then I'll let you know. I have another meeting which should end by then, I hope. So 11, let's say a meeting at 11 on Sunday.
Okay.
Okay. Okay, can we resume back? Is there any around? So 2 minutes. Can we come back? Who's around? Raise your hand, or because not everybody has a camera, so I do not know if you're on or not. One I see. Other people? Shangang, are you around? Ofek, you're around, I see. Shukai, there were other people and they're gone. I don't know why. Is there some communication or you don't know?
I don't know. I'm home.
You're at home. Okay. Well, we're all going to be at home for the next few weeks, right? Okay, so the weak interaction. Now let's resume. So I told you last time we're dealing with the weak interaction that in some basic sense it's much more interesting. Well, yeah, much more interesting than the electromagnetic and strong because it contains several interesting features, right? So one feature which we already discussed was this mixing, right? That the W plus minus bosons, while they do not mix leptonic generations, they do mix quarks generations. And the guy to incorporate that into one single theory was Khabib, right? To show that we can still treat the quarks as doublets, right? But the same way as we treat the muons, right? So we have a muon doublets, nu e e, nu mu mu, nu tau tau, right? But for the quarks, we cannot have that because for the W can mix quarks of different generations. So I simply changed the basis. I just wrote down quark doublets U D prime, C S prime, and T B prime, rather than D S and B. So D S and B are the mass eigenstates. These are the ones that appear in the Hamiltonian, right? And D prime, S prime, and B prime are the interaction eigenstates. So these are the ones that appear in the interaction, and they are related to the mass eigenstates by the Khabib Matrix. So Khabib originated when he wrote his theory back in 1961, I think. There was only 3 quarks known, U, D, and S. So we just wrote down D prime and S prime as cosine theta Khabib, sine theta Khabib, minus sine theta Khabib, and cosine theta Khabib, D and S, right? And that enabled to generalize, right, the same interaction. So for example, D and U bar, W minus, right, L and anti-neutrino. This will be G cosine theta Khabib. And then S U bar, this will be the pion, right? And this will be the kaon, S U bar. G sine theta Khabib. So you could explain how come the kaon, which is a different particle than the pion, still can decay into lepton and anti-neutrino, but with a different probability, right? Because the coupling constant now is different, right? It's different by the ratio is tangent theta Khabib. And more than that, he was able to predict the the decay rate of the other baryons, right, such as the lambda. So it was a great achievement by Khabib. Again, at the time that there were only 3 quarks known, and then in later on, Kobayashi and Maskawa generalized to the Khabib's idea and the Khabib matrix into 3 generations, because by then there were 3 generations known. So they had D prime, S prime, and B prime. The V, U, D, V, U, S, V, U, V, V, C, D, V, C, S, V, C, B, and V, T, D, V, T, S, V, T, V, V, S, B. Right. This is the CKM matrix, which we discussed already. And the values are measured, right? These are measurable values. And the other thing is that it gives one coherent picture of the weak interaction, right? But now, of course, the verdicts, right, looks like that. You have the DJ, and then UI, and a W minus, there's a VIJ. Right, so you have coupling, you have the weak interaction between particles of quarks, sorry, different generations. Any questions about that? Okay, no questions. Today we have something which is, to me, very interesting. Let's call it the parity violation. So remember, what does a parity operator do? It's an open question, guys. What does a parity do?
They inverse the coordinate.
Exactly. It reverses space, right? P of R goes to minus R. Right? Now, we'll have to be careful. I didn't really fully define it simply because we did not have time. So you have vectorial quantities, right? Such as the position or momentum. They also change sign under parity transformation, right? So if you have a vectorial quantity, right, they change sign. Right, so vectorial quantities such as momentum, right, P goes to minus P when X goes to minus X. Right, so known as vectors. But there is another class of quantities, right, which are known as axial vectors or also pseudo vectors. I don't think we had time to discuss those, right? Axial vectors, also known as pseudo vectors. Right. These are quantities that are formed by cross product of two vectors. So of course, the classical example is the angular momentum. And another example is the magnetic field, which is nabla cross A, where A is a vector, right? So these are formed by cross product of two vectors. So what happens to them under parity? They do not change sign. Right? L, for example, is R cos P. Right? So under parity, it's a minus R cos minus P, which is just L. Right? So it does not change sign. Now, they are vectors in the sense that, we said that a vector is defined by the way it is being transformed under the Lorentz transformation. So they will be transformed like vectors under Lorentz transformation, but under parity, they do not change sign. And that discriminates them from real vectors. All right? You with me? Okay. So, right, I would just say, okay, what happens when you have a scalar vectors of two vectors? Scalar product of two vectors, what do you get? Come on, guys, you know the answer. What do you get from a scalar product of two vectors? What quantity do you get? There's no hidden tricks here. Well,
Scalar product of two vectors or a vector product of two vectors?
no, a scalar product of two vectors. What do you get?
A scalar.
A scalar, right? That's obvious. What do you get from a scalar product of two axial vectors?
Scalar as well.
Scalar as well, right. And what do you get from a scalar product of a vector and an axial vector?
Pseudoscalar.
Exactly. Okay, so if you have two vectors, right, p dot p, you get p squared. This is a scalar, right? P or L dot L, right? This is also a scalar. But when you get I don't know, L dot P, this is a pseudo scalar, which means that they do, if pseudo scalar is supposed to scalar, right? Under parity, it does change sign. Right? A scalar under parity doesn't care, right? It's just a number. But the pseudo scalar does change sign under parity. So the classical example, right? Not just L dot P, but S dot P. So what is S dot P? What quantity that we discussed is proportional to S dot P?
Can you repeat the question?
What quantity that we discussed is proportional to S dot P?
Helicity.
The helicity, very good, H, right? So H, the helicity is a pseudo scalar. It's not a real scalar. So on the parity, it does change sign. Now, both QED and QCD are invariant under parity. That's the important thing, right? QED, QCD are invariant. So for many years, it was thought that parity is a basic fundamental symmetry of nature, right? That means that, you know, all observed phenomena look the same if we look at them directly or via a mirror, right? Not just the one mirror, but three mirrors in three directions, but you got the idea. There is no way for us to tell whether when we see something, it is directly or via a mirror. All right. But, okay, so the simplest way to see that, right, is if you look classically, right? So, for example, classical Lorentz force, classical EM, right? F is Q E plus V cross V, right? So under parity, right, F goes to minus F, E goes to minus E, V goes to minus V, but B, right, B is nabla cross A, it's a pseudo vector, right? So it does not change sign. So if we look at the Lorentz force under the mirror, right, then we'll see that minus F, so under parity, right, minus F is Q minus E minus or plus minus V cross V. So when we cancel the minus sign, we end up with the same thing we had previously. So we cannot tell if we are looking at an experiment, what side of the mirror. So all experiments of motion of a charge in electromagnetic field are invariant under space reversal. Now, I didn't say that the entire QE electromagnetic theory is invariant under space reversal, because in order to prove that, I have to show that the whole set of Maxwell's equations are invariant, but they are. You can check it at home. So the full electromagnetic interaction is invariant. Now, another way of thinking of that is to think of the fact the Lorentz force, it's a vector which is equal to the sum of two vectors, right? So I can think of it, right? I have a vector which is equal to the sum of two other vectors. So I have a vector which is C1 times vector V1 plus C2 times V2, right? And since all three vectors change sign under parity, then the direction and the magnitude of the measured quantity relative to the physical quantities of the experiment is not changed. Right, you with me? Yes or no? Okay. Now we can say the same about axial vectors. So if we have an axial vector, A, which is a sum of two axial vectors, right? Then we have exactly the same situation, right? Then it's invariant under parity, right? So, can be the sum of magnetic fields, the angular momentum and magnetic field. That's fine. No problem. Of course, what we call parity violation right? This can exist only in a theory that contains expression which mix the vectors and axial vector, right? It exists only in a theory that contains expressions of the form, right? X is some constant, CV times a vector V, plus another constant TA times an axial vector A. Makes sense, right? So when we try to basically add a vector to an axial vector, then what we get is a theory that is violating parity, right? So under parity, right, P of X would be minus CVV plus CAA, right? So obviously this is different than minus X or different than X, right? So for many years, it was thought that parity, that all physical quantities are made of either vectors or axial vectors, and they don't mix. So it pretty much came as a surprise that the weak interaction does mix them. You with me? Yeah? Okay. Okay. Now, just as, again, notation, right? If we have that CV is much greater than CA, or that CA is much greater than CV, right? Then we say a weak parity violation, right? Parity violation is weak, right? Then if CV and CA have the same magnitudes, then we say it's a maximal violation. Right? That's the maximum difference between X and P of X. Okay, so now let me tell you a story, right? So the first evidence, so if we go back to history, right? The first evidence of a possible parity violation that means that the first evidence that parity may not be a symmetry of nature came with an experiment with the kaons, right? So the kaon were discovered in 1947, one of those particles that came out from cosmic rays, up and strange. And they were discovered in a cloud chamber, right? That's the older detectors that were used at that time. And the kaon decay into pions, pi minus plus pi plus plus pi minus, right? Now remember that in one of the previous tutorials, we found that the pions are eigenstates of the parity, right? With the eigenvalue, do you remember what's the eigenvalue? It's -1, right? We had this tutorial a few weeks ago, right? I just remind you, right? We had the consideration of the interaction of the pion with the deuterium, right? D plus pi minus goes to 2 neutrons. It was a little bit of a technical calculation, which ended up that we showed that the eigenvalue of the pion is a -1, right? Now we know that today that it's reflected in the quark model, etc. So the pion is made of the quark and anti-quark, and in the ground state, L is equal to 0. And then the Dirac equation requires that the fermion and the antifermion have opposite parities, right? Remember all that? Very quiet. Yes, no, maybe?
Yes.
Yes, good. I hope so. Now, okay, so this for the 2 pions, it was by 1947, it was, or a few years later, I think, it was measured that also these 3 pions decay also are in the ground state, which means that the parity, since it's conserved, P of the kaon minus has to be -1. Again, consistent with the quark model, no problem. Right. Now, several years later, I think it was 1952 or 54, I'm not sure. There was another particle that was discovered, which looked the same as the kaon, right? It has the same charge, the same lifetime, the same everything, but it only decayed into 2 pions. Right? So later there was another particle, right, which decayed into 2 pions, right? Pi minus plus pi 0. And they're also in the ground state, so L is equal to 0. That means that the parity must be +1. Now, since people thought that the parity, at that time, people thought that the parity is a good symmetry of nature, then they concluded that these must be 2 different particles. They cannot be the same particle, although they look exactly the same. As far as people could measure, same lifetime, same charge, same everything. But one decays into a state with a negative parity, and one decays into a state with a positive parity. And so they got different names, actually, right? They count, this was called the tau. That was fine because the tau lepton was not known by them. And this new particle was called the theta. It was called a p tau minus is a -1 and p theta minus is a +1. So they had 2 different names just based on that. But they were still quite puzzled by the fact that they look so much the same. The people did not think it's a coincidence. All right. And then in 1956, I think I mentioned that Li and Yang, or Yang and Li, right? They proposed that the weak interaction, right? This is the one that's responsible for both decays, may not be conserved parity. In 1956, it was Yang and Lee. They came up with the idea that the weak interaction is not conserving parity. And if this is the case, that means that what's called the tau and the theta are really a single particle, which is the count, right? So tau minus is the theta minus is just the count. They just say that there is this single particle, the count, that has two different decay modes when changing the parity. And what nice thing is that they show that all the experiments that were conducted until that point could not rule it out. And so the same year, it was conducted a new experiment. That's the Wu experiment. Again, a lot of Chinese scientists were involved. So this is Xian-Xiong. I hope I spelled the name properly. It's Xian-Xiong Wu. So it's Xiang-Xiong Wu. She was a Chinese. It's a she. She was a Chinese, and she worked in the U.S. in Michigan. Argonne National Lab, I think she was. She did the experiment to check that, right? What they did is to study the beta decay of nucleons, right? So she took cobalt-60, which decays into nickel-60, plus electron, plus anti-muon, anti-neutrino, sorry. Now the cobalt nuclei, they possess a permanent nuclear magnetic field. They were aligned in a strong magnetic field, right? So you have the cobalt nuclei, right? They have a strong magnetic moment, mu, and they put them in strong magnetic field, B, right? And there were detectors that look at the different polar angles in which the electrons, so she was just looking at the electrons. So the electrons, E minus. And if there was a parity conservation, then it should also go in the opposite direction at the same rate, right? Because if we do a parity, right? So if you put a mirror, right, do a B, then you know, the nuclear nu, and then the electron should go in the opposite direction. Now, B and mu, they are axial vectors, so they do not change under parity. So the only quantity here that can change sign is the momentum of the electrons. Right, so anything that only quantity that can change sign is the momentum of the electrons. So if parity was conserved, right, what did it mean? It means that the rate of electrons that are being emitted at a certain direction, right, relative to the magnetic field, should be identical to the rate of the electrons at the opposite direction, right? R1 and R2 should be equal. Okay, you're all with me? Okay. So experimentally, what she found out is that this is not the case, right? That result led to the Nobel Prize for Li and Yang. So basically more electron emitted in the direction opposite to the direction of the magnetic field than in the direction of the magnetic field. So this was the first clear proof that parity is not conserved in the weak interaction. So that means, in QED and QCD, we had these 4 currents that connected the fermions, right? We had the J mu, right? U prime P U bar P prime gamma mu U P. So we cannot have that. Right? Another way of seeing the same thing, right, is just to have, okay, so we have a this is the z-axis. If we place everything along the z-axis and we put the cobalt here, right, which decay into a nickel plus an electron and an antineutrino, right, be the same direction, then it means that the in order to conserve the angular momentum, the total angular momentum, so to conserve the angular momentum, the electrons and the antineutrino spins have to be oriented in the same direction, which is upward, right? So the electron, let's say, go in this direction, and the antineutrino in this direction. But in order to get the conservation, then the spin has to be oriented in the same direction. Which means that antineutrinos always positive helicity. The helicity states of the antineutrino as dot P normalized. Antineutrino is plus 1/2. So when we put that in Dirac equation, right, and the spin operator in Dirac equation of the particles and antiparticles is related by the minus sign, remember that. That means that the neutrino always have left-handed helicity. That's another consequence of this experiment, sorry. And it was later on discovered that the same applies for the other neutrinos, right? This was for the electron neutrinos. So all the neutrinos are left-handed, all the antineutrinos are right-handed. Again, this is experimental fact. There was a few, last year there was some claim that this may be somehow related to the fact that DNA in our bodies is, the helix is right-handed. It's quite cool. All right, I think we went out of time. I still need to speak about the masses and then the Lagrangian and the gauge symmetry. But you can see that the gauge symmetry here is not going to be as simple as it is for the other the strong and the electromagnetic interaction. It's much more interesting, but I think I'm going to wait with that. And then we'll speak about the hypercharge and the unification of the weak interaction with the electromagnetism, so the electroweak interaction. But I think this will wait for next week. Any questions?
No.
No? Are you all aligned with me? We still have 2 more weeks to go, and I think there's some really, really cool and interesting stuff, but it's a bit technical, so it might be require, you know, to put attention. So, you know, keep a close track on the ongoing. If you have any questions, please don't hesitate to ask, and I am giving you the next problem set. Yeah, try to make it, because the plan is to give you another one next week. All right.
Thank you.
Thank you very much.
Thank you.
Stay safe. There is now a quarantine. So please stay safe and stay healthy. And keep on the good work, I guess. You know, if you have any questions, then don't hesitate to ask me. Especially now that things are getting closer to the end of term.